everyone. Today we're going to be learning about potential energy, which is energy that can be used to do work, but isn't doing work yet. As we'll see, it can take on a number of different forms. In this picture, for example, there's a lot of potential energy in the bows of these arches. It's not doing work yet, but it's probably just about to. So potential energy is stored energy. That's one way of thinking of it. While it's stored, it's not able to do work. There are many different types of potential energy, and it turns out all of these can be changed into other forms of energy, where they can be used to do useful work. In this case, a mousetrap, we have potential energy stored up in the spring of the mousetrap. And when the trap is activated in the right way, that spring will release all of its potential energy and transform it into the kinetic energy of the trap. So this is called elastic potential energy. Elastic potential energy is the potential of an object to spring back into its original shape. So for a spring, for example, if we push it together, then we're giving it potential energy. And when we were to let go, that potential energy would turn into kinetic energy and it would spring back into the shape that it started in. It turns out we can do the same thing if we start off by stretching the spring. Once again, the potential energy that we'll give it will be able to make it snap back into its original shape. So when a spring is squeezed or stretched, it gains elastic potential energy, and when we release it, it will lose that potential energy and convert it into kinetic energy. Remember, with the conversion of energy, we cannot create or destroy energy. We can only change it into different forms. Chemical potential energy is the potential of an object to react in a chemical way. We use this sort of thing a lot in chemical reactions, if you do chemistry. In a reaction that absorbs heat energy, called an endothermic reaction, it means that the system will be gaining chemical potential energy. You're putting heat into a system, and it's being used up by the system. And what's happening is that heat energy is being stored as chemical potential energy. It means that we have a new sort of chemical that has that potential energy stored up inside it. This potential energy can be converted into electrical energy or into heat energy. If you ever conduct a chemical experiment where you get energy released, it means that by changing into a different sort of chemical, the chemical that you start with is losing its chemical potential energy and converting that to heat. In the case of a battery, instead of converting the chemical potential energy to heat, the chemical reaction produces electricity. Finally, we have gravitational potential energy, which is what we'll be focusing on the most while we're studying space and gravity in particular. Gravitational potential energy is the potential of an object to fall. If an object is capable of falling, or even of rolling down a hill, then it will have gravitational potential energy. When an object is lifted above the ground, it gains potential energy. We can see this ball over here. As it moves up from the ground, its potential energy increases. At the same time, it gets slower and slower, which means that its kinetic energy decreases. So it means that the kinetic energy of the object is being transformed into potential energy. The movement of the ball is being changed into a potential for the ball to fall down. And so when a ball does fall down, it's converting that potential energy that it has hanging in the air into kinetic energy. And in doing so, it loses all of its potential energy as it transforms into kinetic energy. It turns out the total potential energy of the objects is equal to the work it takes to make them that way. That means that if we do a lot of work to lift up, for example, a huge boulder, then its total gravitational potential energy will be the total work that we put into it while we lift it up. Remember that due to conservation of energy, if we put in a certain amount of energy, that energy can't just disappear. It's stored as the potential energy of the object. Work can be calculated with this formula. Work equals force times distance. That means that if we lift something up higher, or if we push something for longer, it means that it will gain more potential energy than if we don't push it as far. And if we have to push it harder to get it there, it means that there will be more energy done actually moving it to that position. Make sense? So F is the force on the object required to move it, and D is the distance that it moves. Work is a measure of energy. The amount of work that you do on an object is the amount of potential energy that you're giving it. So to lift an object at a distance of, say, h for height, we have to exert enough force to overcome the weight of the object, right? Otherwise we can't move it at all. You can imagine that some objects, of course, are very massive and therefore very hard to lift. So the work done to lift up the object is given by FGH, right? Work equals force times distance. So if we lift up an object a distance of h, we have to overcome the weight force. We know that the weight force is mg, so this gives us an altered equation for the amount of work it takes to lift up an object. That work, and therefore the potential energy that the object gains, is equal to mgh. It'll be a fairly important equation. So the work on an object is a measurement of energy. Force times distance gives Newton times meters, but it turns out that 1 Newton meter is equal to 1 joule, the SI unit of energy. So the potential energy that the object gains is equal to the amount of work done on it. Gravitational potential energy is therefore given by exactly the same equation as the work it takes to lift an object up a distance of h. So the gravitational potential energy at a distance from h from the ground, so you're able to fall h meters, is given by mgh. That's how much work it takes to lift something. That's how much energy it will have when it comes back down. At a planetary scale, we can't use that equation for F. We can't use F equals mg because the gravitational acceleration will change depending on how far away we are from, say, the planet, right? So instead we use this equation. Gravitational force equals the gravitational constant times the product of the two masses over the distance between them squared. This should look familiar by now. So it means that the work needed to separate the two planets by a distance of r, because that's the distance between them, is given by this equation multiplied by r. One of the r's cancel out, so we end up with the work it takes to separate the two planets is equal to gmm on r. Make sense? So if we start off with the moon on top of the Earth and we lift it up that distance, it will have this much potential energy. And so if it were to fall all the way back down to Earth, this is the amount of kinetic energy it would have if it landed. So as the distance between two bodies increases, the potential of the object to fall also increases, right? Because it can fall a further distance. If we were to use the approximation work equals mgh, which works near the surface, we can see that as height increases, gravitational potential energy increases. So as a rocket launches from the Earth, the force on it will decrease less and less as it travels out to, Jupiter or wherever it's going. But the gravitational potential energy will still be increasing, just more and more slowly as you get further out. And in fact, when we reach an infinite distance, that means that we're so far away from the object that we're not feeling any gravitational force at all. For our equation of gravitational force, imagine what would happen if the distance, r, equaled infinity. The force would be zero, right? So that means that at an infinite distance, we in fact have no gravitational force, and this means that we have no gravitational potential energy. So hang on, what happened here? We started off by lifting something up, and as we lifted it up, it gained more and more potential to fall, but when we lift it up an infinite distance, it has zero potential to fall. That's odd. So it turns out the gravitational potential object increases until it reaches a maximum of 0. So if the maximum value of a variable is 0, what does that tell you about the variable? Well, it's got to be negative. Otherwise the maths just doesn't work. So an object's absolute gravitational potential energy, that is taken from the frame of reference an infinite distance away, is given by negative gmm over r squared. So if we take the surface of the Earth to have a gravitational potential energy of 0, so we say that this is 0, then as we get further and further away from it, we'll gain potential energy, and our potential energy will be positive, right? But if we say that infinity has a gravitational potential energy of 0, and as far as we can tell it does, that means that gravitational potential energy will be negative. That means that our 0 is over here. And as we fall closer and closer to the Earth, our gravitational potential energy goes down to a negative number, until finally we land on the surface with a gravitational potential energy given by this equation. So whether gravitational potential energy is positive or negative all depends on what you define as 0. If you say 0 is the surface of the Earth, here, then it means that gravitational potential energy will always be positive. If you say that at infinity, gravitational potential energy is 0, then your potential energy will always be negative. Alright, so that's the end of the theory. In this section we've covered exactly what potential energy is, and some interesting facts about gravitational potential energy. So let's go on to some questions. Question 6. A satellite launched into orbit has far more gravitational potential energy than it did on the surface of the Earth, right? Its potential energy is greater. What is the source of work done on the satellite to make it gain this energy? If we're making something gain energy, we need to do work on it. So we have options: the gravity of the Earth, the gravity of the Moon, solar power, or the rocket engines. So all we have to do here is ask, what exactly is lifting up the satellite? The answer to that seems fairly obvious. It's the rocket engines of the rocket used to launch the satellite. The satellite gains potential energy when it is put into orbit, and the work is done by the rocket that puts it into orbit. Remember that the source of the work being done to lift up the satellite is the rocket engines. So that's where the potential energy comes from. Question 7. Which of the graphs best shows the relationship between the gravitational potential energy of an object and its distance from the center of the Earth? So in a question like this, we're going to assume that we are in fact moving a fairly large distance away from the Earth, and not just, up a few meters. That means that the force on the object will change as we go further away. The equation that we want to use to model this is g m m over r. This will be our potential energy, right? So obviously, if we have 1 over r, or a constant over r, then we're not going to get a straight line. That would happen if it was proportional to r. So right away we can rule out options C and D. Our other two options are A and B, right? In both cases, the gravitational potential energy of the object is slowly approaching 0 as we get closer and closer to infinity. So this is right. If we get close to infinity, then we get closer to 0 gravitational potential energy. But what happens closer to the Earth? Do things tend to have more potential energy when they're close to the ground, or more potential energy when they're lifted up from the ground? The answer is they have more potential energy when they're lifted up, of course, which means that our potential energy increases with distance. The best answer then is A. So we can see that A is the correct answer. Question 8. A satellite of mass 150 kilograms is orbiting 722 kilometers above the Earth's surface. What is its gravitational potential energy? We'll use this as the radius of the Earth, and this is the mass of the Earth. And this is our equation for, of course, the universal gravitational constant. So what's our equation for gravitational potential energy? That's right, it's minus gmm over r. All right, so we can substitute in our values, g, m, m, and hang on, what's r? R is going to be the radius of the Earth plus the altitude of the satellite above the surface. So we'll have the radius plus the altitude, and it's in kilometers, so we need to multiply it by 1,000 to get it in meters. All right, so this equation seems fairly straightforward. Let's evaluate that. It turns out to be minus 8.43 times 10 to the 9 joules. This is quite a large number, so you can see that there's a huge amount of work that needs to be done to launch a satellite into that orbit. Question 9. A boulder weighing 850 kilograms, ooh, heavy boulder, sits on top of a hill at an altitude of 11 meters above the ground, so it's probably a fairly shallow hill. If we were to draw a diagram, it might look something like this. When in doubt, diagrams are always helpful. There's the boulder, and we're 11 meters above the ground. Right? So if the boulder rolls down the hill so that all of its potential energy is converted to kinetic energy, then how fast will it be moving once it reaches the bottom of the hill? So in this case, we're looking at changing potential energy into kinetic energy, right? Now the question says we change all of the potential energy into kinetic energy. So what does that mean? It means that EP equals EK, right? Initial potential energy equals final kinetic energy. What's our equation for kinetic energy? That's right, half mv squared. So our gravitational potential energy, mgh, equals half mv squared. We can cancel out the m's, assuming we don't have a massless object, and multiply both sides by 2 in order to get v squared equals 2gh, or taking the square root, v equals the square root of 2gh. So, what are these values? G is, of course, gravitational acceleration, we all know that. And our height is going to be 11 meters above the ground, sometimes referred to as altitude. So we can substitute those in. We'll end up with square root of 2 times 9.81 times 11. And using a calculator, we can evaluate that to 14.7 meters per second. Multiplying by a factor of 3.6, we have roughly 40 kilometers per hour. So the boulder will be moving quite fast when it reaches the ground. Question 10. A proton in the solar wind travels away from the sun to the Earth. The Earth is this distance away from the sun, one astronomical unit. Assuming the radii of the two bodies are negligibly small, so we don't have to worry about the radius of the sun or the radius of the Earth, how much gravitational potential energy does the proton gain due to the sun? Remember, it's moving away from the sun, so its potential energy will be going up until at an infinite distance it reaches a potential energy of 0. So we're given the mass of a proton and the mass of the sun. The symbol for the sun is sometimes given by this symbol. It's been used since ancient times. So, how do we find the change in gravitational potential energy? Well, all we need to do is find the gravitational potential energy at both points and find the difference between them. So the change in potential energy will be simply the masses times the gravitational constant times the divided by the difference between the radii. That is the distance between the proton and the sun. So our initial distance from the sun is 0 because we're coming out of the sun. Our final distance is the distance when we reach the Earth, 1 astronomical unit. We can now substitute in our values, and that'll look really messy, so I'll just go straight to the answer. 1.48 times 10 to the minus 18 joules, which might not seem like much, but remember that this is a single proton. It turns out that by the time it reaches Earth, it's slowed down by about 40 kilometers per second, just because all of that kinetic energy has been converted into potential energy. Of course, it's still moving extremely fast when it reaches the Earth. This represents only a small fraction of the proton's energy. Alright, so that's the end of the questions, and it's the end of the lesson. So in this section we've learned about gravitational acceleration and how to measure it, as well as gravitational potential energy, how to estimate that, and how it's converted into different forms of energy.